Hey, so today we actually get into the heavy duty stuff and kind of bring it all together. And the polynomials that we're going to find zeros for and factor are just going to get um, like crazy loco. So I hope you're excited for that. Uh, I know that I am. I'm sure that the Boosh is. Um, so here we go. Okay, so um, what we're going to take on next is the fundamental theorem of algebra, and that's not going to be too taxing on us. But by the name, they call it the fundamental theorem. You can guess that it's pretty much a big deal, um, and it is. And what we are saying, what this is going to tell us is that if we have a polynomial of some degree n, um, then that polynomial has at least one zero in the complex system, and it has precisely n zeros. So if we have a function that is a fifth degree, then this has precisely five zeros. A couple of them may be complex, a couple may repeat. So it's going to have five. Um, and furthermore, we know that if it has five zeros, we can also write it as five factors. So now it doesn't tell us how to find them, kind of leaves that up to us. Um, but it tells us that they're there. And we've already seen ones where we've had repeated zeros. The only new thing really is the complex part. So let's take a new polynomial here. Ta-da! And let's list all zeros and factor completely. Okay, so if you ask Renee, he's going to say one, two variations in sign, so we are looking for two or zero positive reals. And if we see, if we change sign, we have minus, minus, plus, 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 plus. So we have one negative real zero. And our possibles, if we do constant over leading, we have 1, 2, 4, and 8, plus or minus, of course. So let's go to synthetic division. Let's pick one, and let's just start with 1. Be a good place to start. Let's see, we have 1, leave a space, 1, 2, negative 12, and 8. And we're going to try 1. So let's see, bring down, multiply, 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 bring down. So I have x equals 1 is a 0. Of course, that means that x minus 1 is a factor. And I'm going to take a crazy guess and try it again. Let's see, 1. So 1 times 1. So multiply, bring down, multiply, bring down, multiply, bring down, multiply, bring down. So x equals 1 is a 0 again, so it repeats. So x minus 1 is a factor again. We know now not to look for any more positives. Let's try negative, and with a lucky wild guess, I'm going to try negative 2. Multiply, bring down, multiply, bring down, probably bring it down. Okay, so x equals 2 is a 0, which means, oops, negative 2 is a 0, which means x plus 2 is a factor. Okay, so we started with a 5th degree. This got us down to a 4th degree. This got us to a 3rd degree. This is the quadratic, so we can stop synthetic division, unless you are really into it. And we are left with x squared plus 0x plus 4, which is just x squared plus 4. Okay, so what we want to do is what we would usually do is we would usually try to factor this and get our last two roots. And if it didn't factor, we would go to the quadratic formula. Well, it does kind of factor. It's just not the kind of factoring you did in algebra, because see, we can't factor this over the reals, but we can factor it over the complex numbers. So check this out. X squared plus 4. I'm going to replace the plus sign with an equivalent minus minus, right? Because what did negative, the two negatives together is a positive, right? So all I've done is, well, I haven't done anything. I've renamed that plus. Now it looks like the difference of two squares, right? So I could call it x plus the square root of negative 4, x minus the square root of negative 4. Okay, well, the square root of a negative number, we can't leave things like that. So let's fix that. So I have x plus 2i, x minus 2i. Square root of 4 being 2, and I being the square root of negative 1. So now we have our other factors. And we could also say if x plus 2i is a factor, then x equals negative 2i is a 0. If x minus 2i is a factor, then x equals 2i is a 0. So for our list of factors, we have x minus 1, x minus 1, x plus 2, x plus 2i, x minus 2i. 1, 2, 3, 4, 5. 5th degree polynomial, 5 zeros, 2 of which are complex, 2 of which are repeating. We kind of get, everything mixed into that one example. I like that. Yes, the factoring was a little weird, but I don't think it's that too crazy for us. You could always try to set it equal to 0 if you don't like that whole factoring thing, and try to solve that. I just have an x squared term, no x to the first, so I would isolate, take the 4 to the other side, and take the square root of both sides, and I have x is plus or minus the square root of negative 4, which is 2i, and here we go again, still plus and minus 2i. So either way, that's all good. So pause this, rewind it, check it out again, check it out 2 times, check it out until it's fully marinated and you're feeling pretty groovy about it, and then we're gonna move on. Okay, notice that 2 of our factors were x plus 2i and x minus 2i. 2 of our zeros were negative 2i and plus 2i. Those are conjugate pairs, and if you have complex roots, they're going to occur in conjugate pairs all the time. Okay, so if you factor something and you get 2 plus 3i as one of your zeros, 2 minus 3i is going to be one of your other zeros. So they always occur in conjugate pairs.